The universe is vast. It is filled with wonders we can see. We see brilliant stars burning with the light of 1 trillion nuclear furnaces. We see swirling galaxies, cosmic islands holding billions of suns, each one a potential home for life. We see colorful nebulae, the beautiful clouds where new stars are born and old ones lay to rest. Our telescopes can peer across billions of light years, capturing photons that have traveled since before the Earth was formed. But the story of the cosmos is not just about what we can see. The greatest part of the story, the vast majority of the universe, is hidden from our view. It is a profound and humbling thought. Imagine everything you can see. Every star, every planet, every galaxy, every speck of dust floating in the blackness of space. Now take all of that, all the normal matter, and understand that it makes up only a tiny fraction of what's really out there. The universe we observe with our eyes and our instruments is just the shimmering tip of a colossal cosmic iceberg. Most of the universe is made of something else entirely. It is something that does not shine, does not reflect light, and does not interact with us in any familiar way. We call this mysterious substance dark matter. It is the ghost in the cosmic machine. So, what is this dark matter? In the simplest terms, it is a form of matter that we cannot see. It doesn't emit any light or energy, which is why we call it dark. It isn't dark in the sense of being a black color. It is dark in the sense of being completely transparent to all forms of light. It passes through normal matter, like you and me and the Earth itself, as if we weren't even here. You can't touch it. You can't taste it. You can't build a telescope that can see it directly. But we know it's there. We know this because of the one thing it does interact with: gravity. This invisible substance isn't just a minor component of the cosmos. It is the dominant ingredient. For every pound of visible matter, the stuff that makes up stars, planets, and people, there are more than 5 pounds of dark matter. It is everywhere. It forms a vast, invisible scaffold upon which the visible universe is built. It is the silent, unseen majority. Understanding dark matter is not just a side quest in astronomy. It is fundamental to understanding the past, present, and future of our entire universe. Its discovery was a revolution, forcing us to rethink our place in the cosmos. How can we be so sure that something we cannot see actually exists? The story begins with galaxies. In the 1970s, an astronomer named Vera Rubin was studying how spiral galaxies rotate. She expected that stars far from the galactic center would move more slowly than stars closer in, just like the outer planets in our solar system orbit the sun more slowly than the inner planets. This is basic physics, a simple calculation of gravity based on the visible stars and gas. But that is not what she found. Instead, she discovered that the stars on the edges of galaxies were moving just as fast as the ones near the center. This was a shocking observation. The stars at the outer rim were moving too fast. Based on the amount of visible matter in the galaxy, the gravitational pull should have been far too weak to hold onto them. At those speeds, the stars should have been flung off into the blackness of intergalactic space, like children flying off a merry-go-round that is spinning too quickly. The only way these galaxies could stay together was if there was a huge amount of extra mass, a massive halo of invisible stuff providing the extra gravitational glue needed to hold everything in place. This was the first powerful piece of evidence for dark matter. Another clue comes from a phenomenon predicted by Albert Einstein: gravitational lensing. Einstein's theory of general relativity tells us that mass warps the fabric of space-time. A massive object, like a huge cluster of galaxies, can bend the path of light that passes by it, acting like a giant lens in space. When we look at very distant objects behind a galaxy cluster, their light is bent and distorted, sometimes appearing as multiple images or stretched-out arcs. This is gravitational lensing in action. It's a powerful tool for astronomers. When we measure the mass of a galaxy cluster by observing all the light from its stars and gas, we get one number. But when we measure its mass by looking at how much it bends the light from objects behind it, we get a much bigger number. The amount of gravitational lensing is far greater than the visible matter can account for. This discrepancy tells us that the bulk of the mass in these clusters is invisible. It is dark matter, bending space-time with its immense gravitational influence, even though we cannot see it directly. It is a cosmic mirage that reveals a hidden reality. So, If we can't see dark matter, how are we trying to find it? The search is one of the most exciting and challenging endeavors in modern science, taking place on Earth, under Earth, and in space. One approach is to try and detect it directly. Scientists have built incredibly sensitive experiments deep underground, in places like old mines or tunnels beneath mountains. They go deep underground to shield their detectors from cosmic rays and other radiation from space that could create false signals. These detectors are essentially very quiet, very clean rooms designed to catch a ghost. These deep underground labs contain giant tanks filled with special materials like supercooled liquid xenon or germanium crystals. The idea is that out of the billions and billions of dark matter particles that are thought to be constantly streaming through the Earth and through you, one might, just one, occasionally bump into the nucleus of an atom in the detector. This collision, as rare as it might be, would produce a tiny flash of light or a minuscule vibration. Scientists are patiently waiting in the dark, watching these detectors for that one telltale sign of a dark matter particle finally interacting with our world. Another way to hunt for dark matter is to try and create it ourselves. This is the work of giant particle accelerators like the Large Hadron Collider at CERN. Here, scientists smash beams of protons together at nearly the speed of light. The immense energy from these collisions, governed by Einstein's famous equation E equals mc squared, can create new particles. Physicists carefully study the debris from these smash-ups. If dark matter particles are created, they would be invisible and pass right through the detectors without a trace. But they would carry away energy and momentum. Scientists look for events where the energy and momentum after the collision don't add up. If some energy appears to be missing, it might be a clue that it was carried away by invisible dark matter particles that escape detection. It's like trying to solve a puzzle with a missing piece. You know the piece is gone because there's a hole where it should be. This missing energy signature is a key way physicists at the LHC are searching for evidence of dark matter production, hoping to glimpse the laws of physics that govern this hidden sector of our universe. Why is this invisible stuff so important? Because without dark matter, the universe as we know it simply would not exist. Dark matter acts as the universe's invisible skeleton. Before the first stars ever ignited, dark matter was already there. In the early universe, tiny fluctuations in the density of dark matter began to clump together under their own gravity. These clumps formed vast, invisible halos or wells of gravity. The ordinary matter we see, the gas that would eventually form stars and galaxies, was then pulled into these dark matter wells. Without the gravitational head start provided by dark matter, ordinary matter would not have had enough gravity on its own to clump together and form the large-scale structures we see today. The beautiful spiral and elliptical galaxies that dot our cosmic landscape would never have formed. The universe would be a much more uniform, diffuse, and frankly, boring place. It would be a thin soup of hydrogen and helium gas, with no galaxies, no stars, no planets, and therefore no us. Dark matter was the cosmic architect that laid the foundation for our galactic home. Imagine for a moment a universe without dark matter. The galaxies we see would fly apart, their stars flung into the void. The great clusters of galaxies, some of the largest structures in the cosmos, would dissolve. The cosmic web, the intricate filamentary structure that galaxies trace, would never have been woven. The story of cosmic evolution would be entirely different. Life as we know it, which required the heavy elements forged inside stars, which in turn required galaxies to form, would have been impossible. We owe our very existence to this mysterious, unseen substance, and yet it remains one of the biggest mysteries in all of science. We know more about what dark matter is not than what it is. It is not made of the same particles, protons, neutrons, and electrons that make up us and everything we see. It is something new, something exotic, something that lies beyond our current understanding of physics. The quest to identify the dark matter particle is a journey to the very edge of human knowledge. Unmasking its identity will not just solve a cosmic puzzle, it will usher in a new era of physics and forever change our picture of the universe. The hunt is on.